EMG. Security.
You know, Xbox 360 was ahead of the time. You know, you could make your avatars have prosthetic limbs.
Oh, really?
Good morning.
Morning.
Oh, not a very full room today. Oh, alright, good. They're open. I'm going to open the other side to get some traffic. How's everybody? Good.
Yeah.
Anyone feeling not so great? Stressed? Tired?
Stress.
He's on it. He's not comfortable today. He may not be in this class today.
That's the first rule. By robotics.
Do you want to come to
By robotics. Yeah. Don't talk about it.
Right. Don't need to do anything.
No, I don't think I'm going to be doing any
Yeah.
work.
Morning. Where's Yusuf? Yusuf.
There he is.
Hi, morning. What is that? Alice.
Is that the remote?
Fancy.
Mouse?
Oh, look. Oh, it is a mouse. Look.
Just like a... it's working.
Hold on, I'm going to turn it on from somewhere.
There's a sneak going on. Is this part of it?
You want...
Although I guess that's the computer, I just need the screen.
Yeah, you need the screen, but I might need the computer later. Why is it not on? Alright, okay, so you can connect your laptop to HDMI.
Yeah.
Right.
Where is it this?
Is it? You have such a weird, cocky voice today.
Weird.
It
Is that
comes
the
and
lingering
goes.
thing from
No, it's new.
when you finally stopped being sick?
You know, it's been a really difficult week.
Elbow.
I
Again?
stopped taking, yeah, no, it's really bad. I stopped taking on so much.
Yeah.
Somehow I'm really bad at it.
That might be like a PhD project.
Why is this not
Maybe that's to be
working?
on the scope of maths. That's the kind of thing. Is like
No, but yeah, for you, but I want to turn...
So
Oh,
there's like this project. Which,
Did that do something?
it just...
maybe, like, everyone's going, yes, we've got people who
This doesn't look-
basically are volunteering themselves.
Yeah, but we did that.
But it's not.
Like, it's only really allowed between all of us.
If you want power, there's all the price. Do you want power?
It should be alright.
Is it a new laptop?
Yeah, this is a new one, so
Okay.
it should,
I
should
forget
last.
Who are the presenters for later? 1, 2, 3. Do you have your presentation on the laptop that you can connect? Because the PC doesn't seem to be turning on. Okay. Okay then. I'm going to... Where are you?
Cool.
Good. Great. So welcome everybody. Good morning. And today is end of week 4. 2 more weeks until reading week, right? And then I'm gonna change what's happening in this class a little bit. So this is our third from last seminar. And we have the very great pleasure of having Dr. Joe Luca. So he's senior research associate at the University of Bristol. And he specializes in trustworthy telemanipulation for high-risk environments, that is surgical, space, nuclear. His research combines robot perception, haptics, and computer vision, realistic simulations, user-centered design to improve how people interact with robots. He has collaborated with the European Space Agency, Thales Alenia Space UK, which is a company who works on the space robotics domain, and clinical partners to help translate research into practical solutions for the real world. And he has also been in a astronaut simulation facility for 2 weeks.
He has.
That's
Well, 1
my
week.
addition.
The other week was a holiday.
Okay,
So-
1 week.
But we could call
Right,
it
take
2.
it away.
All right. Hello, everyone. Okay. So yeah, I'm Joe. I'm going to talk to you about designing robots that we can trust in high-risk environments.
we'll talk about lots of things. You know, what is trust in the first place? Why does it matter? We'll look at some of the theory behind it, and then get into a bit more of the practical side. You know, how do we design a robot that we can trust, and verify and validate that it is trustworthy? And then I'll tell you about my research in space applications, on how I actually implemented that, in real life. So we'll start with what is trust, and it can be quite a vague concept. It includes lots of different factors. I mean, if we asked any of you to describe what you thought trust was, I'm sure each of you would come up with something different. So there's loads of models out in the literature that people have come up with. They tend to include similar sorts of things. So this one here splits it into 3 different aspects. So human-related factors that impact how people trust a robot, robot-related factors, and environmental. And these are kind of internal and external as well. So you've got in the, can you see my mouse here? Yeah. In the human-related side, we've got things that are baked into the person, and same with the robot. You know, how good is the robot, and then sort of looser qualities. How does it respond to the environment? And then similarly, here's another one that's a bit more interesting. Splits it into 3 sections again. You've got the disposition of the person, so that's your kind of your basic factors about the person. You know, what's their culture, what's their background. Then you've got the person in the situation. How confident are they? How much do they understand the subject? What mood are they in? And these are a little bit more dynamic. And then the external ones, so outside of the person, what matters that might influence their trust. So how hard is the task? That's probably going to change your perception of whether you trust your robot. And this side is quite interesting as well. So this really captures that trust is not a static thing. It's going to evolve over time. So generally, it's very slow to build trust. Quite quick to break it and damage it, and then rebuilding it is slower after that. So you want to make sure your robot behaves well and doesn't harm trust over the course of people using it. So you start off with an initial level of trust. You know, you might say you bought a robot from the shop. You have an understanding of the brand. You have some previous experience with similar robots, so you've got a baseline, and you think, yeah, no, I think it's going to behave this way. And as you use it, it's going to evolve, whether it works or not, how reliable it ends up being, how many errors you end up witnessing. But yeah, the important bit in these two models is that there are loads of factors that impact trust, and we've got to somehow capture these when we're designing a robot that will be trusted. Which is not always easy. So based on not just these 2 models, but lots of different definitions in the literature, I've come up with these 2 definitions. And it's important to set your definition at the start of your research, because especially for something vague like trust, you need to say what are we actually measuring against. So this definition of trust is a willingness to use a system based on confidence that it will behave as expected without negative consequences. So it's the attitude of the user. Trustworthiness, on the other hand, is the property of the system. So is the system worthy of your trust? Does it behave as expected without negative consequences? And it's not enough for the system just to be trustworthy. It needs to show the user that it is trustworthy, so it needs to demonstrate it. So you can have a system that is perfectly safe and reliable and effective, but unless the user believes it to be that way, it's not going to be used. So yeah, this gets onto like why do we need trust in robotics, and it's really down to robotics is a very real world subject. We want to make things that people are going to use. If the people don't trust it, and this can be the person actually driving the robot, or the people commissioning the robot, or implementing it on a much larger scale. If they don't trust the robot, then it's not going to be used, and that's really the important thing. So a very simple example of a system that you might be designing, your phone camera. This is very simple. You press a button, takes a picture, saves what was on the sensor. There's a little bit more to it than that, so you don't know when you press the button. Well, say you had a system with no feedback whatsoever. You press the button, how do you know that your photo's been taken? Or you're lining up your picture, and how do you know when the right moment is to press the button and take your photo? And you need what we call non-functional requirements, which are parts of the system that don't really affect the functionality, but they're important for its use. So in the phone, you might have, for example, it will make a shutter noise, or the image will flash slightly, and just give that little bit of feedback to the user and say, okay, the job's done. You don't need to hammer the button over and over again. It's just a little bit of feedback. I mean, this is a pretty low risk situation, so consequences aren't that bad if you take 1 million photos. But say you're making a contactless payment. How do you know that your payment's gone through and the right amount? Well, you get a little beep. Your phone might give you a notification and say, "Yep, you've paid 20 quid." And without that, how do you know not to keep tapping your card on the machine? Or how do you even build confidence in the first place that you're going to use contactless and not go back to cash? So these are very simple systems, but the same principles will apply if you're designing a more complicated one. And we can't really leave it to chance whether it's down to the individual's individual disposition or mood or their experience. We need to do whatever we can and control the parts of the system that we can control as robot designers to kind of stack the odds in our favour that people are going to want to use the system. And again, sort of making this balance between, you don't want them to trust it too much if the system is actually not very good, and you don't want to under-trust it if the system is better than they believe it to be. So I don't know if any of you have come across this concept of designing for X. It's a systems engineering concept. It's basically saying consider the capability, the aspects of your system that you want to bake into your design from the very beginning. So you say, if I want to design for manufacturability, you think about that early on when building the system, not after you've developed your product and you're like, oh wait, well this is impossible to manufacture at scale, and you have to go back and redesign it. So it's really considering the important parts of your system from the start. So if you're designing for costs, you might make sure you can use commercial off-the-shelf products, components, and just sort of bake them together, or serviceability, and make sure you can take it apart and put it back together, that sort of thing. And we could do the same thing for trustworthiness. It's just another aspect of the system. It feels vague, but if you can define it, and if you start from the beginning and say, well, we'll define what needs to be in the system to be trustworthy, then we can make sure that once it's developed, it should be as we planned it. So this could include factors like reliability, transparency, so that is making the robot's decisions obvious and understandable, kind of making the user feel like they understand the robot's perspective, safety parts of things, ethical sides of things. There's lots of different bits that come under trustworthiness, but if we capture them at the beginning, then we can make sure that we meet those requirements. And then again, you might have seen something like this before, verification and validation. So this is, again, more systems engineering. You start on the left-hand side of this V is your design side. On the right-hand side, you've got your testing side, starting at high-level requirements, moving down to the system and lower into individual modules, components. And then on the right-hand side, you test it. And it's really making sure that you have built the right thing. And, well, if you verify it, your verification is checking that you have built the thing right, and then your validation is checking you have built the right thing in the first place, so checking your requirements actually achieve what you wanted to do. And yeah, your requirements are what the system must achieve, and the specifications is how they're going to achieve it. So the robot needs to lift heavy objects is the requirement. Specification is it will lift 5.5 kilos with 0.1 millimeter accuracy, and you can check that this is actually the case. You can measure it. Yeah, and once you've got your specification for trust, you can test against all these factors and make sure you're meeting the right requirements. So we'll move on to my application. So this is, as Tonya said, I focus on space applications. Two main ones that I'm interested in are surfacing satellites and collecting moon dust. So if you collect moon dust, you can build habitats and you can extract oxygen or water and good resources out of it. And I'm looking at the teleoperated case. So this is where you have essentially a person driving the robot rather than automation. So on this scale, from supervision to autonomy, it's quite over on the left-hand side. The reason it's slightly away from the edge is when you're in space, you're so far away from your robot, you will have a communication delay. So if you're on the moon, it's 2.6 seconds best case return journey at the speed of light to communicate with your robot. So you send a command, and then the robot will do it, and you can't intervene until 2.6 seconds later in the best case scenario. I mean, it's probably more than that with all the relays, satellites, and everything. So there's an element of you're committing to your task, and you need to delegate that responsibility to the robot that is going to perform the task as expected. Automated robots are going to be used a lot in these applications, but you're always going to need that human guidance for edge cases and recovering from errors and stuff like that. So this is why I've focused on the teleoperating robot side of things. And you can really imagine, if we go back to the definitions, so if we want our users to trust the robot, they need to be willing to use a system based on confidence that it's going to behave as expected without consequences. So negative consequences, we can picture what they're going to be. In space, it's very expensive, it's very hard to get there, you don't want to break the robot. The user obviously needs to be willing, else they're not going to take that risk, because they might get fired or they might lose lots of money. And then they're behaving as expected. If you've got this delay, then you really need to predict how the robot's going to act. So you can see how trust is probably going to be important in this scenario. So that's what I focused on for my PhD. These are the delays we're talking about. If you're going to Mars, it becomes completely unmanageable to do teleoperation. But in this sort of area, which is where a lot of activity in space is at the moment, there's heaps of stuff going on in low Earth orbit, and we're moving towards the moon. So it is becoming quite relevant. So I started off going back to the V diagram. We'll start on the left-hand side, and we'll capture the requirements for what is a trustworthy robot. So spoke with experts from different industries. In different industries, they're already carrying out teleoperated tasks. They're doing high-risk applications. So in underwater scenarios, quite similar to space, you've got a remote floating free-body robot that will be doing maintenance tasks. Defence, ordnance disposal, you can see how that's obviously going to be risky. Nuclear decommissioning, there's a huge safety aspect to this, and a lot of that work is done using teleoperated robots rather than automated. And then surgery as well, so you obviously don't want to accidentally chop someone up the way that they're not meant to be chopped up. I spoke to experts from each of these areas and asked them, what features, experience, evidence do you need to trust your robot? Would you ever let the robot take the lead, or do you want to kind of have your hand on the stop button the whole time? And really trying to capture what are the non-functional features that help or hinder you when you're carrying out your tasks. This is the methodology that I used to sort of quantify this and make this a little bit less vague, so you can have some weighting behind it. So of all the interviews that I carried out, separate into segments of what they discussed, what they mentioned, prioritize them. Is this MSCW, so that stands for features you must have, features you should have, features you could have and will not have. So it's kind of a hierarchy of importance. Group them all up into themes, add a score to them, and then you work out your requirements based on that. And this is, another systems engineering method that you drag through, and you can, it's good when you're designing complex systems with lots of different factors. So I collated it into themes, and it really, four main themes came out of it. The first one was that users really need to understand their system's capabilities and limitations. So this is about the user. It was interesting that I was expecting a list of features. I want haptic feedback. I want visualization. I want it to be autonomous in these situations. But no, the first thing they wanted was to understand what their robot's doing. It's not about the robot. It's about them, which links back to the models of trust. They did mention improving situational awareness. This was mainly through lots of different camera views. Some people mentioned haptic feedback, some people didn't, so it was a bit of a mix. And coming from the dexterous robotics route, where we look at haptic feedback a lot, I was a little bit disappointing. The third point here is facilitating operator training. Again, focused on the operator, not on the robot, and easing the cognitive load of the operator. And that was really about having a support team there, making sure supporting information is provided to the user without obstructing them while carrying out their tasks. They want to be able to focus on one aspect of the scene, so they want to look at their main camera, drive their robot, and people can feed in information as needed. So it was kind of surprising. It made the research a little bit more difficult because I was hoping they would say, we want haptic feedback, and I could test haptic feedback. That's not how it went. So in this situational awareness, we've got the different viewpoints, and there was mixed views on haptic feedback, so we had a look at that anyway. But this is what I'm going to talk about for the rest of it. So in the training side of things, they mentioned firstly that they want to test and train with gradually increasing risk and realism. So this is starting off in a nice benign simulation environment, moving into a physical mock-up, and then gradually moving into the real world. So and increasing the task difficulty and all of that. Which is interesting because it's quite hard to do that on Earth, because you can't build a physical mock-up of something in 0G because we have 1G here, so it's not going to work. And then they also want lots of hours of experience witnessing the robot functioning as expected without fault. And how do you do that when you've only got a couple of systems up in space? So how do you provide the right amount of training for people to get over that threshold of we're willing to use this in the real world? So it kind of all pointed towards simulations, really. I mean, I'll talk first about the initial test with haptic feedback. This was a very simple task that we set up. So it was a user study to validate whether haptic feedback was indeed useful, identified it as a requirement, so now we're going to check if it works. We asked them to complete 2 tasks. Draw where have we got here? So here's the robot. On the end of it mounted a pen, and this isn't maybe on this picture. So the aim is to first draw a line along the groove, and then insert the pen in the hole. And we did this with different delays to see how people responded. This is the control diagram, just for clarity. So there's force feedback controlled via this haptic device, and as positions and forces, that arrow is meant to go the other way. Past this delay threshold, then you apply half the delay, imagining it's gone to the moon and come back, stuff like that. We did this with 0 seconds, 600 milliseconds, 1500 to 600 millisecond delays. That basically covers from orbit up to the moon, just to see where, if there was a point that people could cope with the delay up to moon level. delays, and basically found that haptic feedback switched from being helpful with 0 delay to being kind of a hindrance, pretty unhelpful as you added the delay. And that's because, you can imagine if you're driving your arm and you move into a wall and the robot senses that force, but you don't feel that force immediately, you might be doing a completely different action, so you might move away, and then 2 seconds later you get nudged to move the other way. You get no sense of how the environment feels, so it actually becomes pretty unhelpful, which was surprising. But we did find that trust is negatively impacted with delay, so it was kind of half successful, this experiment. Looking at the training side of things, we went back and thought, how can we meet these requirements with this barrier if you can't have haptic feedback with delay? So one possible method is to use something called model-mediated teleoperation, which is quite a mouthful, but it's basically, instead of this control diagram where you've got your feedback and commands passing through the delay barrier, you move that to the left and have the robot interact, or the user interact with the simulation, and then the simulation sends commands to there. So you kind of keep the control loop on the local side, so there's no delay, and hope that the simulation matches reality, which is, it's a big assumption that your simulation is going to match reality, but this was basically what we decided to test. So this moved away from satellite servicing and moved on to the moon dust collection, and started from scratch and said, right, well, if you're gonna build a model-mediated teleoperation system, you need a simulation. If you're interacting with moon dust, it's quite strange. It's cohesive. You're doing it in 0 gravity. It gets everywhere. It's the worst material you're ever going to work with. It's got this like electrostatic charge that means it sticks to like all your tools. It's a pain. So there was a simulation developed not by myself, by some researchers in Germany who basically modelled simulation based on astronauts' footprints and other very clever stuff that I'd never be able to work out. And it approximates it. Instead of being fine, dusty material, you get these little balls. And hopefully, here we go. So you can change the gravity, the density, the stickiness, and the friction of the balls. And on the left, we can see 3 different materials. So we've got ball bearings, simulant, and sand. And then the same thing just happening under moon gravity. And you can see, I'll just play that one more time, hopefully. So the regolith sort of stops and starts as it goes through. It's got this weird flow behaviour. So we wanted to check firstly whether this simulation is at all accurate. So that ties into the verification side of things. So we tested against a physical experiment and the virtual experiment. So the top one is the physical. We got some simulant of the regolith, poured it through some funnels of different thicknesses, did the same in simulation, and then did the same thing with some larger funnels. And basically the important bit is we're checking the flow rate is the same, so if we're going to use this in a robot system, then it will behave normally. This red line is data from physical tests, and the black lines basically track with it. So we check first at the low level that our component is good. The simulation is verified to be accurate, so we can move on to more interesting tests. The whole system one. So this is where I worked with the European Space Agency at their lab, and basically built the system into connected it with a robot. So where's my mouse gone? On this side you can see the nice little simulation of moon dust with our scoop, and this is the actual arm doing the scooping in a task, and this was to simulate like sample curation, tasks. So if you get your sample of moon dust back from the moon, you don't want anyone to touch it because we want to make sure it's completely clean and it will all happen in a vacuum chamber, and it all needs to be done remotely. So it's not quite the delayed teleoperation example, but it's a good way to link up with ESA. And here we go. So this is it in action. And to verify, this stage was all about verifying the system. So is the system trustworthy? We need to make sure that the regolith is scooped for the task. It spills a little bit. And we need to make sure that it pours. We need to make sure that any indentations you make in your simulation are represented in the real world. So we've got this little dent. If you're going back to scoop again, if your simulation doesn't show that, then you might go and scoop and actually scoop nothing. And then that would damage trust because your robot wouldn't work. And it turns out that it works pretty well for an approximation that could be run in real time. But yeah, the main thing was to evaluate whether it was trustworthy. So this is a bit of a jumble. But looking at it again, back to the definition. So trustworthiness, does it behave as expected without negative consequences? So we can call the virtual environment the expectation, and the physical environment the behavior. So does the simulation match reality, basically? If it does, then it's trustworthy. If it doesn't, then it's not. And we found that it was successful 92.5% of the time, with false negatives, so where it scoops, it manages to successfully scoop in the real world, but the simulation, it doesn't work. That only happens 7.5% of the time. So
could you explain the 4 definitions? Because I think they appear a lot for medical robotics as well as this, and I'm not sure that people understand false positive, true positive, and all that. Do you understand what false negative is? Is there anyone who's not sure? Could you maybe explain?
Yeah, so you've got, let's see if I can explain this. So you've got 4 possible outcomes when you're testing things. So you've got we'll call this side the ground truth, and this is your test result. If your ground truth is kind of a pass, a success, and your test result is a success, then you end up with what's called a true positive. So your test matches the result, the actual result, and same with the true negative. So you want your test to match both of them, really. You want, if you've in the example of medical tests, say you've got I don't know, some test for a disease, you want to make sure that if you've got a positive result on your test, that correlates with a positive result on your that you've got the disease. Yeah, and the same with the other one. If it's negative, then it means you haven't got the disease. But some tests kind of are weighted a little bit more towards they give more positive results even when you don't have the disease. So that would be a false positive, and the opposite way around of false negative is where it says you don't have the disease, but actually you do. And in this case, the behaviour of the simulant, the real world, is our disease, and then the test result is the simulation. If that kind of makes sense. Yeah. But yeah, and this sort of grid pops up all over the place in like hypothesis testing as well. So it's I don't know, you can kind of apply it to lots of different things where you've got binary outcomes. So it's quite useful. Yeah. So we got our requirements. They said simulations might be useful, so we developed a simulation, checked that verified that it was accurate on a low level, verified that it is trustworthy as a system. So the next step was to validate whether it actually improves trust with a user involved. So we set up 3 test conditions. DT, which is direct teleoperation, so this is just like that first haptic feedback test where you've got the feedback passing over the delay. VM, which is a visual-only model-mediated teleoperation, so you just see the video of the simulation, and HM, where you get some haptic feedback from the simulation as well. And we tested with like 30 people in a user study, carrying out a similar sort of task to the one with ESA, scooping from that pot, putting it in the container, and seeing how people responded. So this is a video of it working, hopefully. Yeah, so I think on this side, so this is a direct teleoperation side, and you can see it's much less smooth. When it flashes red, that's people colliding with the walls, so they don't really know where they are. It's all a bit more wobbly. They pause a lot of the time, so this is known as move and wait behavior. So it's when you've got a delay, you move, you wait to see what's happened, you check your feedback, readjust, and then move again. So you get this kind of jerky behavior, which in the real world would be an absolute pain because you can't do anything smoothly. Everything takes a lot longer. And I wanted to know whether you can use this behaviour as a measure of trust. So up until now, I've just been using questionnaires at the end of the task, which obviously have limitations. I think, is this going to play? Hopefully. Yeah, so you can really see the move and wait behaviour. You've got the direct teleoperation on the left and a model mediated on the right. So I think this move and wait behaviour is kind of, you don't trust that your robot is going to carry out your task correctly, so you split your commands into little chunks, and if you can measure the behaviour of someone, it becomes much more subconscious, so you don't get user bias when they're just completing questionnaires. Or, I mean, a major thing, I mean, you guys might do some user studies, I guess, in when you get onto your project. Fatigue is a real problem with people, particularly if you've got a long experiment and they have to complete a questionnaire lots of different times. They get bored, they just start ticking like 5, 5, 5, 5, 5 and just go down. So your data's not always that great. If you can also measure the behaviour of them, then yeah, you can get a little bit more detail out of it. But you need to check that the behaviour is actually what you want to measure, which is not always the case. So these are the results. On the green one is direct teleoperation, and then the other two are the two model-mediated ones. So you can see there's not really a huge difference between haptic and visual feedbacks, which again was kind of surprising, a little bit disappointing because I wanted this to work. But maybe it just doesn't matter having haptic feedback for this task. But in all of these, you do see a difference between the direct teleoperation and model mediated, so where they're using the simulation. This is a questionnaire score. There's a clear jump in how people believe they trust their robot, and then so this is how this metric, for example, is how much are they moving as a ratio of their total time. So they move proportionally more when they're using model mediated. I mean, this is, yeah, it's a big jump. And then comparing the behavioural metrics against the scores, we do get this slight correlation. So it's probably not strong enough that you can definitely say this is measuring trust. But it's, yeah, it could be an indication, and if you combine it with the questionnaire, then it sort of adds weight to your argument that you are measuring what you say you're measuring. But another problem that you might come across when you're doing user studies is actually getting the participants to really buy into the test. So we've got no guarantee that that they actually cared about the experiment. Like, some people were doing it and they were pretty rough with the robot. They were moving things around. They didn't care if they collided with things. It was all fine. Some people were very cautious. So you got, yeah, it all kind of goes back to individual differences and everything. And there's no guarantee that what we were measuring wasn't actually being oblivious. So if you've got no idea what the risks are and you don't care if anything bad happens anyway, then you're just, yeah, you're ignorant to the whole thing. You might be reckless. you might know full well that there are going to be some risks, but you don't care. So you carry on. Same with cautiousness, the other way around. Yeah, you might think there's no risk, but you're really concerned with bad things happening anyway, so you're naturally more cautious controlling it. But yeah, it's just something to look out for when you're doing experiments. Is, I don't know, put yourself in the shoes of the participant and think like, how could I ruin this if I'm not in the mood for it? Because they will, they will do that. But anyway, yeah. So we've gone through the whole stage basically. We check the component. We verify the component is trustworthy. We check that the system is trustworthy, and now we validated it and measured that the system does improve trust. The next step was to go in the field, and this was my trip to Hawaii, where I tried to test the robot in a field environment, see if the simulation works, and it turns out it completely doesn't, because the robot was rubbish, and this dirt is not at all like the dirt I was using. So I had a nice trip, but it it wasn't very good science. And they made you dress up as spacemen when you go outside, so that was pretty cool.
What was the correlation of choosing Hawaii?
There is partly it's just very nice.
Yeah.
Yeah, so they have these, they're called analog facilities, so they're like basically pretend Moon, Mars bases where people train to be astronauts. There is one in Yorkshire that is underground in a mine. I didn't apply to that one. I applied to Hawaii. But yeah, so this is on a volcano, which is actually, it went off quite a big eruption a couple of years ago. So I don't think realistically we should have been there, and I think this base might have closed down since. But because it's on a volcano, you've got these like lava fields. You can you're not meant to explore the lava tubes, which are like caves underground, but you have a little look. And yeah, it's just a completely alien landscape, so this is why they use it for training, and it's way more interesting than going underground in Yorkshire. So yeah, but yeah, I mean, there's all sorts. There's some in Switzerland and Iceland, and they're always looking for participants, and some of them, I think the European ones might be free as well, so it's worth having a Google and seeing if you fancy doing it, because it's yeah, whilst you've got time, you might as well. It's a nice way to spend a week. But yeah, that's all I've got for you. So any questions?
Maybe I'll start, and then I'm sure you're thinking about lots of questions. So you did loads of user studies. You did quantitative ones and qualitative ones.
Yes.
What are the challenges of each?
Qualitative, the data analysis is really, really hard. Not necessarily hard, but it's hard to be objective when you're looking at. So in the interview study, when you've got just pages and pages of transcripts, how do you make sense of that? How do you compare what one surgeon was saying with what a bomb disposal expert was saying? And sort of, you want to make connections, but you don't want to force the connections and sort of see results that aren't actually there. You're just trying to make a story out of nothing. So that side of things is quite hard, which is why I came up with that quite rigid procedure to make sense of it. The quantitative user studies I think it's the same problem, but from a different aspect. So you still need to do data manipulation to, I don't know, if you're recording sensor data or like the path of the user, there's lots of data you're going to record that is quite messy. So making sense of that is still difficult, even though you think, oh, I'm recording a number. It's just going to be I get a 10 or a 5, and you can make sense of that. And it's like, how do you iron your results out that they make sense without overworking them, that you've cooked the data up and sort of found your own results. So that's quite important, I think. Recruiting people is quite tricky across all of them, so they're kind of similar. You need more time if you're collecting deeper data, but you can get away with having fewer people in. But yeah, it's really it's a trade-off. Ideally, you get both types of data in whatever you're doing, but yeah, it's not always practical. So
how about the first user study? I remember that maybe it was basically that you got results and then you had to discard everything
Yeah.
and then change the methods.
Yes, people will try and break your experiments without a doubt. So the first user study I had was that drawing a pen along the groove task, and you've got your 3D controller that gives you haptic feedback. And the idea was they'd move down slowly until they feel contact, and then sort of move forwards along the groove, feeling the contact as you go, and sort of taking it nice and seriously. But we had so many people, and I didn't realise it until like halfway through the 20 people doing this experiment. They would move very slowly down to the surface until it's pretty much lined up the pen with the groove, and then they would rest their hand on the table and just like whoosh it forwards, and you're like, whoa, you're really good at this, how are you doing this? Because I was watching the robot, making sure it wasn't crashing, and you've got to have your hand on the stop button. So yeah, I didn't realise that was going on.
But I guess it's about, I think that, I mean, they were clever, they found a way to do it,
Yeah.
but we couldn't understand the questions, the answers to what we wanted to ask, and then we realized we were asking the wrong question.
Yeah.
So it's about doing what you can until you understand what is the correct question to ask,
Yeah.
and then, get the results for that.
Yeah, you can get distracted by building a nice thing, so making your robot do something that you think is cool. But really, you need to check what the question is and then almost do the minimum you need to do to answer that question, rather than get bogged down in details. Because we're not making a shiny product; we're just trying to answer individual questions, and that makes your research much more manageable. But yeah, it can be less exciting to go and do all the I don't know, like gaming out an experiment and seeing how someone could break it. Yeah, make sure you get pilot studies done. So get one of your friends to try out the experiments who hasn't seen it, and just see what they do, see if they react, because they're not going to behave the same way that you do using the robot every single day. That would be the biggest tip.
Other questions, please?
Just going to say, what was your undergraduate background before coming into sort of this field?
So mine was in biochemistry, basically. So I had a real mixed background. I did my undergrad sort of, probably started my undergrad nearly 10 years before my PhD, and then worked a little bit in various places. Did a master's in robotics. Went and worked as a systems engineer for 2 years, which is why there's loads of systems engineering stuff in there. But yeah, my background's in biology and chemistry, so switching to robotics wasn't easy at the start, but then it's such a mixed discipline. It's useful to have all these different perspectives, I think. And now, I mean, programming is getting so much easier that you can just ask the AI to make you a program if you have a rough idea of what you want it to do. You can learn it quickly. So yeah, is yours? I'm guessing yours is not an engineering background.
It's computer science.
Oh,
so
okay.
it's,
Yeah.
Adjacent. But,
Yeah.
I was just looking at all the user studies and everything, and this is essentially my undergraduate. Is just I had to do so many studies and reports and just with people interacting with applications, and I guess it's the same sort of thing with systems.
Yeah.
So it's just there's a lot of correlation there. That I'm I know exactly how to do this. This is, yeah.
Yeah. It's the same. My master's. One of my friends, their background was in psychology, and we came into it thinking oh, this is going to be impossible. But actually, the experimental procedure is so baked into them in psychology. They really understand how to set up an experiment, do the stats tests. They understand the process of it. So he was really good at it. But yeah, once you just get around the technical side of things, it's.
And then, are you down as a dissertation supervisor?
I think I will be. Yes.
Yeah. What sort of projects would you like to be approached with? What sort of interests you have, I guess?
Yeah, so at the moment I'm working in surgical robotics now. So I'm doing a project that is based on 2 robots. One does ultrasound guidance and one is needle insertion. So there's lots of different aspects of that, from image processing to data generation is quite good. Accessing real patient data is difficult. So if you can generate artificial ultrasound data to train a neural network, that'd be brilliant.
And you can do trustworthiness for that.
Yeah. Oh, yeah. Yeah. If you can work out how to do that, that would be good. Because I mean, I like research that has an application. I don't love all the abstract bits that float around. I mean, I know trustworthiness is dead abstract, but if you can work out a way to help research turn into reality, then I think that's really important. So new devices. So I forgot my list of. I did have a list of projects that I was thinking about before I came in, but I can't remember. But send me a message.
Absolutely.
Yeah. Equally, if you've got a space robotics project that you want to do, I can see if I know about it, and still interested in that side. Just there's not a lot going on at the moment, so yeah.
How would you you spoke about how people would like not care or were reckless with the robot and stuff. In future research you would do in trustworthiness, how would you improve that sort of thing? How would you make the people care more about it?
Yeah, that's a good question. I
We
think.
discussed some fun ideas. Remember with the Top Gear.
Oh yeah, well, like a leaderboard.
Yeah.
Yeah. I think rewards, leaderboards, any way that can like publicize if someone's really bad at something. I mean, you don't want to bully them, but some people are so competitive that they'll get into it. I think that side of thing is if you go back to.
Promised an increased thank you voucher.
Yeah.
If you do really well.
Well, like, so this side of the scale is quite easy to fix. So if someone's reckless, you just need to make a way of them caring. So you can give them a reward, you can give them a leaderboard, like, and if they're reckless, there's a good chance that they're competitive. So they will, they'll probably buy into that one. If they're, you can make people.
I'm not sure if all these are really ethical though. So we would have to really.
You need to check.
Check them, with the.
It probably depends how you pitch it.
Yeah.
Yeah.
Give them a shock every time.
Yeah, good classical method that. If you don't know about the risk, you can educate people about the risks and be like, really don't like. You can ham it up a little bit and be like, this robot's really fragile. Do not break it. It will cost loads of money. You'll ruin everything. Like, people do have a line where they do start to care a little bit. But I think the trickier bit is how do you get someone out of the cautious zone and into trusting? And I guess that's kind of what the research is trying to do. Like, how do you make it so someone's happy to use the system even if they're not familiar with it? But when you've only got half an hour for a user study, like, how do you really develop that? I'm not sure. I think maybe you would do a larger sample of people and almost filter out based on some questionnaire at the start their attitude to robots and see if you can.
I mean, if anyone is from a human factor background, because we have a very mixed background, some more biochemistry and biology in here already. You could just have a project where you have 5 different groups and you give a different reason to each of them to care. One is a leaderboard, the other one is increasing reward of money, the other one is I'm going to tell you about why you're going to destroy my career if you break the rules, just appeal to ethics and emotional, something else, and then see which one works better. Maybe there's literature on that as well.
Yeah.
So, like, jokey follow-up question to that suggestion. If you had people genuinely sign that it was okay, could you ethically shock someone? Like, those, like, lie detector things where it, like, buzzes or something, like, where it's a very small... Like, could you have people sign up
like
to...
deception,
sort of like negative reinforcement instead
say
of
that
positive.
you're going to electrocute them, but you don't want to actually do it.
Well, yeah, if you have them sign and agree that, like, they're okay with that.
So, I
Do you
don't
think
think
ethically...
the ethics of university will not allow you to electrocute them.
Okay.
It might allow you to deceive them by basically saying that you're real but you want.
Right.
But at the same time, that will trigger a much bigger process, so it's probably not going to be easy
Yeah.
And also it's been done, and people, will they believe you that they will actually electrocute themselves? I don't know.
You could like have I could have an actor, Josh, be like,
It's
okay,
been
so
done,
he
though,
gives a
hasn't it?
demonstration and then he does it wrong, he gets shocked, and then
But it has been done.
I think on your form you'd have to, you'd have to write down and
Yeah,
say
of
like,
course.
oh, I'm going to do this, and then they'll be like, but they already know that works, so don't do it twice. Like, don't set up a prison in your basement and set some people up as the leaders and the prisoners.
No, I just think, I was thinking about this with some of the other lectures, just how, there was one talking about that guy who had a monkey, didn't feed it, would it prefer the fur or the food, and it chose the fur. It's like, that's not ethical because it's not a real monkey, but it chose the comfort of its mum. Science went a lot faster when we weren't ethical.
Yeah.
Well,
And I mean,
why the teleoperate robots are designed to use swans to transfer something? Is to imitate human behavior or just more easier to simulation?
so why is it designed to collect the dust? Was that?
To use something like a swan. Not, I think because some other behavior like grasp or other behavior maybe more like the robotic.
Yeah. So I think this was a really simple task. This was basically imagining that you've got a really small sample and you just want to move something granular from one to the other. We were testing the simulation rather than interesting designs of the end effector. There were other people at ESA who were looking into how do you make an end effector that can scoop something but also grasp. So if you've got rocks mixed amongst it, then you've got a more versatile end effector. So I think it's more human-like behaviour would be something that can grasp, but you don't always need to do it. I mean, you can also collect things without an end effector at all. You can use a conveyor belt or vibrations or something. So there's I actually think a lot of robotics aims towards grippers maybe too much where you don't need it, but I mean, maybe, don't know, that's still up for debate. So it's like the whole humanoid robot thing is, there are lots of humanoid robots out there. Yes, they fit in the slot that people have got, but if you're making a factory, do you need a humanoid robot or do you need lots of machines working together that can do it much more quickly? I don't know, it's up for debate. Sorry, does that answer your question? Yeah.
okay, do we have any burning questions? Otherwise, we thank Joe. Thanks so much.
Yep.
Okay, shall we take 10 minutes break and move around? So come back in 7 minutes past 11. And whoever has a laptop to do the presentation, maybe set up in the meantime. Thanks so much.
It's valid. Well,
It's valid. I was just thinking of operation. Right.
I think
like Michael Reeves. Yeah. Where he's like, big taser guns and shit.
James would taser us. I'm thinking like, it'd be fun. There's little group activity. To be fair, like if it's like a little like a stinginess or something. That's what.
Sting like suck, but
Yeah, like come on, like you're not gonna die.
I'm thinking like those like
Like if I were to pinch you, like a little pinch, like a robot that pinches people.
sure, yeah.
Yeah.
Yes, we do a novel way of torture. It's not actually like inside they have a
Novel torture.
There's no ethics against it yet.
I'm just gonna lie you down and have something drip on your forehead periodically.
I'm gonna have a robot tap you on the forehead.
Yeah,
For a new client, every spy agency.
It's like you know those YouTube videos where it's like 2 hours of silence with bangs. I think you should do that with a robot. So it's like you capture heads, and then every like 1 in a million chance see if people trust it.
Yeah, well, the robot that every couple of hours just drops metal pipes.
Robot that drops metal pipe.
Elongated Russian roulette. I say no to Russian roulette. I like your science food a lot faster.
I mean, it did. It did. Yeah. Like people were just like kidnapping humans off the street, cutting off their heads, and going, and now we have to wait for someone to die and ethically give up their brain, and now their brain's like kind of decomposed, and you have to go around.
It's a bit of the like, oh, you know, humans are like 70% water. Don't ask how we know that.
Yeah.
Yeah, it's also like, you know, I don't know, use death row in space. I'm just saying.
Yeah. Honestly, this should, yeah.
If they're gonna die anyway, just like, hey, we'll give your family like this much money if you donate your body to science. Like you're gonna die anyway.
Oh yeah.
Yeah, you know that guy who had like he was fully immune to it. He kept him, checked him. I'm like the family of the.
Thank you very much. Please present yourselves and title of the paper.
Cool.
And you have 10 minutes, right? I'll time you.
Okay. Hello, welcome to today's presentation. It's covering a research paper that's evaluating the initial usability of a hand augmentation device across a large and diverse sample. So, introduction. So,
Try to look at the audience.
Sorry.
If you need help, look at the screen.
okay.
Try to
So, the researchers are looking at a hand augmentation device. They're looking at the third thumb, which is a secondary thumb for your hand. They cover a bunch of applications that this can be used for. So for accessibility, it will help people with disabilities doing everyday tasks. And in industry, it can increase productivity and reduce injury risk for a lot of activities. They also state that there's a large societal importance for this stuff, where technology needs to be designed to be inclusive and accessible in early R&D stages to benefit all users, especially when we're talking about human augmentation. So yeah, and then the state of the art. So this research is mainly aiming to bridge a gap in research where there's quite a lot of bias in technology in quite a lot of areas. So AI, human augmentation, where it doesn't cover all the people. So more inclusivity needs to be considered in design stages, especially when we're talking about this human augmentation, because it's meant to be used for everyone. So they aim to cover for the initial usability for a large and diverse population, and they hope to pave the way for a benchmark during the development stage for testing inclusive technologies. Cool. Methodology.
The third thumb project was conducted at the Royal Society Summer Science Exhibition in London. Out of 600 people approached, nearly all were eligible, and 579 completed the task, with 97.8% operating successful within 1 minute. The robotic thumb was worn on the honor side of the right hand and controlled by 2 undertow pressure sensors, providing 2 degrees of freedom. Each participant received 1 minute of the onboarding, followed by 2 60-second tasks. Task A involved using only the robotic thumb to pick and place pegs, while task B required collaboration between the robotic and biological hand to move form shape of different geometries. Because the study took place in a public and noisy environment, no parametric tests were applied, along with the bias factor BF to quantify evidence strength. A BF greater than 3 indicates moderate evidence for different whereas a value below 1/3 suggests evidence supporting no difference. The data were also analyzed across age, gender, handlers, and fine motor experience to identify who benefited most from the device. The study noted several limitations. The foot pad fit and pressure celebration were less suitable for young children. Only the right hand was tested and the session provided only a short-term snapshot without a long-term learning date. Future work aims to develop personalized pressure paths, standardized 1-minute onboarding plus 2-task protocol as a benchmark for augmentation device and open the dataset for replication and comparison by other labs and public venues.
Okay, before I move on to the experimental results, let me quickly introduce how the device was set up. The design two sizes are then small, so it can fit different hand sizes, but functionally they are exactly the same. And instead of using the original battery-powered and wirelessly controlled version, they used a simplified design. As you can see in picture C, there are just two plates that can detect pressure directly wired to the system. So it removed some worn parts such as battery packs or pressure sensors, which makes it more convenient for the experiment. The researchers analyzed the results from 4 aspects. The first is wearability. They tested 596 participants in total, aged from 3 to 96. To check wearability, the users could choose the one that fits best, and then they were asked to press the 2 plates to control the thumb, just to check they can apply enough pressure. Out of all the participants, only 4 couldn't use the thumb, either because it doesn't fit well or the sensor was not sensitive enough for very large children. So overall, it worked very well. 99.3% of users could use the device successfully. The picture below shows an 11% sample of all the visitors, just to highlight their diversity, but it doesn't completely match the study sample, so it's just for illustration. Next is focused on how the users performed when they were using the system. In the individuation task, they could only use the system to pick up packs and put them into a basket. In the collaboration task, they are allowed to use any of their natural fingers or palm along with the system to pick up objects. A total of 333 participants completed individuation task and 246 participants completed the collaboration task. Across both tasks, 98% of participants were able to successfully manipulate the system during the first minute of use. And among the 13 users who were considered as unsuccessful, the researchers think they couldn't control the system properly, or simply they misunderstood the instruction. So all these results show that the system can be used easily, almost by anyone. After they confirmed the overall success rate, they also looked into demographic considerations. They applied Bayesian statistical method to evaluate the difference across demographic groups. However, there's no big difference at all. So it means people of different genders, handiness, and professional background were able to use the system just as effectively and easily. The last part is the effect of age. They analyzed this separately because they noticed something interesting, some interesting patterns there. Normally, we are expecting the older adults to struggle a bit more, but actually their performance was almost the same as the younger groups, even up to the age of 96. So to further explore how aging affects the ability to control the system, the participants were split into 4 quartiles, and they put the results and they put the results of the 2 tasks together because this can produce a stronger and more reliable Bayesian factor. Within the group of older adults, we can saw that the performance gradually declined with age. The y-axis represents the time taken to pick up one object, so the higher value, the worse performance. And among younger groups of younger participants, they found, especially under 11, they found their performance improved as the age gets older, which is the opposite trend to what we saw in the adults. So the researchers believe it is very important to figure out what causes this, but they didn't mention it in this paper. So that's all for the results.
All right, let's look at the feature outlook. Well, oh, sorry. All right. So let's start with. I can touch it. All right. Let's start with the first feature direction. Well, looking at how different people get better at using the third sum over times. The paper we studied only tests the people's first try, just 1 minute to get used to it, and then 1 minute to do a task. But the author said clearly we need more research on long-term use and daily habits. So from these results, we saw two things that kids under 11 didn't do as well at first. Is the Q1, yeah, is this one? They cost a long time, and adults over 34 years old get a little slower as they got older, and the paper calls it age costs. But we still don't know if this group use the device for a long time, just like a couple of weeks or months, the gaps will get smaller. So here's what we can do next. As we can see, we should run some studies. We train different groups like 5 to 11 years old children, 12 to 16 years old teenagers, younger adults and older adults. And we will track how fast they finish the task and how many mistakes they make. And also we especially want to check two things. Can kids fix their early struggles with focus of movement practice, always practice? And can older adults lower their age cost with training that fits their needs? And this way we can find and make better training plans to for different groups when we update the device in the future. Yeah. And the second direction is make sure that more types of people can use the device and the device itself can work better for them. The paper's sample was very broad. As it mentioned, it's like 3 to 96 people, 96 years old people and left and right-handed people, but it still had big gaps. The author said we couldn't cover very important groups like people with disabilities or have different body types. So yeah, this is one gap. And also the sensors, the device only has two sizes, big and small, and the pressure sensors didn't work for very light kids. In the paper, 3 of the 4 people who couldn't use the device were kids, too light for the sensors. So this is the second gap. So the next step have 2 parts. First we should let me see. First, we should work with disabilities. Yeah, work with disabilities to test the device with different people. Some people with hand issues, can it help them? And second, we can include some people with different body types to check if it fits all hands of width and length, just like some different body types. Yeah, and also we should fix the device. Make pressure sensors where we can adjust how hard you need to press, so light kids can also use it. And design parts, we can mix and match, just like for some different straps to disabilities. And yeah, and this is a design idea. And also we can test it in real life job, like such as moving heavy things in factories and stuff like that. And alright, this is all our presentation, and thank you all for listening. We welcome any questions.
Thank you. Questions?
So, on your initial demographic slide, I'm sure there's probably not a direct answer, but I'm pretty sure it was about, I think it was the one before this, there was about 28 or something % of people who didn't disclose their age, race, gender, and that's, you know, like, about a quarter of participants. Like, you're losing out on 150 people in that data set. Do you have any speculation into why it is, if the papers address why there's such a high percentage who prefer not to say what this is? Because do you think it would have impacted the data a large amount, or do you think that there's enough with the other, 450 people that it's all still? I just thought
it's
it was
an interesting
yeah.
question. Yeah, I would say that there definitely is the potential to have it affect the thing, but what's quite an interesting thing is obviously gender's quite a big debate in today's society and everything, whereas these researchers are they're looking at what it feels like to be sex rather than gender necessarily. So there's potential that maybe they need to in the future split those groups up separately, so rather than it being just gender, it would be sex and gender or something.
And
the age.
And this picture it's just a sample of all the data and not the study sample. It's not fully overlapped, so they use this picture just to illustrate that their study sample has many different kinds of people.
No, of course, it's just that there's such a high percentage of the study, a quarter of the people have decided not to disclose.
18%.
For age is what I'm
age
referring to. Like 28% of people, and I think that's quite a proportional subset of people. I don't necessarily think that the gender of the ethnicity is as big a concern as the age.
Yeah. No, they didn't really talk about that, I think, covering that. So no, I don't have an answer for you,
That's
basically.
all right, yeah. I was just curious.
Yeah.
Well, unfortunately, we're on this slide. So for the 7% of people who said that they have a disability, was that, did they anywhere in the paper say whether this is a physical disability, like mental, an invisible?
No, not actually. And these 7% of people maybe not in the study, maybe not all in the study sample. So,
but they would have, right? Because this is participants.
Yes.
If 7% they say yes, they were included, no?
Yes, but they didn't.
They didn't specify.
Yeah. Yes.
Well, I mean, if you remember the methodologies, do they say anything about what, is it a hand-related disability or anything?
I think they just say that it's just a disability. I'm pretty sure they don't they want people with hand disabilities.
And they didn't analyze how the disability affects the results.
Yeah.
They just
which is definitely a big gap in the paper.
Gender, age.
See, these are good questions because these are the stuff that reviewers of papers pick and then say, explain this more.
Yeah, because I just think there's so much missing data there that you can't quite say that.
Yeah.
And then as well with the disability, because disability is so varied. You could go from someone like me to somebody who's got some learning disability to somebody who's
And then the question is as well is like, can you design for this is to cover a large diverse population, but can you design everything to work with every disability? Probably not. So then it's the question of, well, what are you picking and choosing, I guess? So how would they do that in the future? I think it's something that they definitely need to cover. Like, what is that device for? Who is it for? And then for who is it for, what are they going to cover? So considering this is a third thumb and the third thumb is really for everyone, they say, you're going to have to look at a lot more than they did initially.
That's kind of the leading thing, is what is the third thumb proposed for?
Yeah.
Yes.
Because
maybe the main customer, maybe the people who lost their fingers, not the normal people.
Yeah. I found that, at least in the video there, people are still kind of using the basis of like their bottom of their wrist to try and determine.
Yeah.
So if there was a missing finger or something, you feel like it wouldn't.
It wouldn't work for them.
Yeah.
Yeah.
Which is definitely why, like Nils had mentioned, I feel like it'd be good for them to have a specific study with.
For sure.
Yeah.
Yeah. Cool. Yep.
Did they investigate the specific method people use to complete the task? For example, they use palm and the third thumb, or they use the one thumb and the robotic thumb. You can see in this video, in the left video, the man use the thumb and the palm, and in the next.
The left video is the individuation task. The man just use the thumb. He's not allowed to use the palm or fingers. But the right one, this lady, she used her palm and the thumb.
The paper didn't specifically like deconstruct how people used it. It was sort of more so you can use it in this way. How did they do it? Basically, how did they like successfully complete it? They weren't like trying to decipher how people use the third thumb. It was more so if people can use the third thumb, basically.
So are they classifying the two ones as the left one they didn't really use a palm and the right one they did?
Yeah.
Because I can see sort of, he is using.
Yeah, it's
No, actually,
No, he didn't use the third one.
It's a pass. You can see just the thumb and.
Yeah, but the palm is used as the wall, the support, something that the finger press against.
Yes.
So in that way, it is used.
well, it's kind of hard.
And
to
I mean,
use.
she's using it in the same way.
I will
She's-
say an an individual task for a thumb augmentation device is kind of weird because you never use just your thumb.
Yeah, no, I agree.
Like.
But I
So what do you think
suppose
for them
my
to
argument is
cover?
that she's doing pretty much the same thing.
Yeah.
She doesn't do much different to the other one.
So what's the point basically of having both of these tests?
And I don't know why they didn't ask all the participants to do the both tasks.
Yeah.
You can see 300 do this task and 200 do this. But why all the participants do the both tasks?
But are they the same or are they different? Maybe the first ones didn't have all time to do both. It's what John was talking about. It's a long time.
But they didn't mention it, so I don't know why.
Yeah, they didn't like specifically say, oh,
So you see, we are like taking apart a really good paper that was published in Science Robotics, yeah?
Yes.
So
it still definitely
there's
is.
so much more stuff you can do.
It's still definitely quite a lot better than what's out there because there is a massive lack of diversity inclusion in technology. So it's a good way to sort of start bridging that gap, but you can already see just in a paper that's talking about it how much you can pick it apart. And really
Imagine how much we
do
pick up your dissertation.
Yeah. Well.
Not to that level. Okay, any other questions? Well, thank you very much then. Okay, so if you bear with me for maybe a couple of minutes, and maybe a little bit more after, these presentations, I just want to remind you the why we're doing them, right? It's for you to learn to present, to be good with communication skills. You will use it when you talk to stakeholders for your group projects. You will use it in other modules, other units, but you will definitely use it in your dissertation. You'll have to present a video about your dissertation topic, your work. And last year was the first year we asked the students to do that, and they all produced a 10-minute video. I can tell you they were not great videos. They were not engaging. They forgot to use images. They forgot to use videos of their work. And I know some of them had videos of like robots moving, but they just didn't put them in.
So is this a video alongside a presentation? Like,
There's no presentation. It's only video. No Viva.
Oh, wow.
Only video and report.
Right.
Unless they change it, but I don't think they're changing it now.
Okay, cool.
It's too late to change
And the
it.
video, does it have to be quite formal still?
Yeah.
Very
Like
formal.
it has to be polished.
Right.
It has to be engaging. So you have a presentation. I mean, you can do whatever you want, but most people do a presentation, and you see a little square of their face basically talking. But you can do interpretive dance. You know, depending on your project, I would very much welcome,
Like
but then, you know, falling asleep.
across.
The other thing is, do not read the slides. Please do not read what's written. You can have a, you know, cheat sheet, and you can read from that if you did, but read it in a way that it doesn't look like you're reading. Have a pace as if you're like casually talking, but you're reading it. I mean, that's what I do when I'm not in front of a crowd. And then in the slide itself, have key words, key phrases, never sentences, never verbs, you know, in a way. Well, never is a strong word to use, but try to make it so people can listen to you, hear what you're saying, and then have this as a visual aid again. Even text can be visual aid. And the other thing, I mean, your presentation was pretty good, but I would say put an image a bit earlier so that you show what people are sort of, you know, about to understand, about to read. And in the same sort of trick we do in papers. I mean, Yusuf will give you specific written feedback, but this doesn't apply just for you. It applies for loads of it and previous presentations as well. A trick we do when we're writing papers is, so usually your images need to be near where you reference them in the text, but a bit of a cheeky thing that we do in papers is that we put them in the first page, even if they're mentioned in the second page, just so, you know, whoever opens the paper sees a title and an image and they immediately sort of understand what the paper is about. So kind of similar thing for your presentations. So that's it. Any questions about anything? Next week I'll release the full topics for each of you on your blogs. Any other questions?
The topics were randomly assigned, weren't they?
Randomly, complete random, and they're as many as you are. I had to even remove some, I think, because last year we had somehow more topics. I don't know. We'll have fewer students. I don't know. Okay, so I'm going to stop recording, and I would like the people who are doing new